Hello everyone, myself Dr. Santanu Kundu. I welcome you all to this lecture of soft computing techniques. This is the fifth lecture of Module 5. So, in Module 5, we have covered selection methods, we have learned crossover techniques, we have also understood the crossover probability and mutation probability. In this class, we will try to understand different mutation techniques. So, in genetic algorithm, mutation is a key operator used to introduce diversity into the population of potential solutions. It helps prevent the algorithm from prematurely converging to local optima and encourages exploration of the solution space. Key features of mutations. First is random change. Mutation involves randomly altering the genetic materials, that is the selection encoding such as chromosome of an individual in the populations. This is similar to how biological mutation occurs in living chromosomes, where random genetic changes can create new traits. Low probability. The mutation rate is typically kept low to avoid excessive randomness that could hinder the optimization process. High mutation rate lead to a loss of beneficial structure found in the population due to the overexplosion of the search space. Diversity. By introducing small random changes, mutation helps maintain diversity in the population. This is crucial for avoiding stagnation, ensuring the algorithm does not simply converge and suboptimal solutions too early. Why mutation is important? It avoids premature convergence. Mutation allows the population to explore different regions of the solution space, preventing the algorithm from converging too quickly to a suboptimal solutions. It introduces novelty, so it helps to create new solutions by randomly altering an existing solution, which may lead to finding better solutions that were not previously in the populations. Mutation complements the exploitation mechanism like crossover, which combine existing good solutions. Mutation ensures that the algorithm does not get stuck in a local minima by introducing randomness. So there are different mutation operators in genetic algorithm. So we'll discuss one by one. So in binary encoded genetic algorithm, there are three techniques, that is flipping, interchanging, reversing. In real coded, that basically formula based, so that is random mutation and polynomial mutation. And there are some other technique in order encoded genetic algorithm. First one is that mutation operator. First one is that mutation operator in binary coded genetic algorithm. In binary coded genetic algorithm, the mutation operator is simply and straightforward. In this case, few 1 are converted to 0 and vice versa. A common method of implementing the mutation operator involves generating a random variable called mutation probability for each bit in a sequence. So if there are 8 bits, so there should be 8 uh, bit in mutation probability. This mutation probability tells us whether or not a particular bit will be mutated. To avoid large deflection, mutation probability generally kept to a low value. It is varied generally in the range of 0.1 by L to 1.0 by L, where L is the length of the chromosome. L, the length of the chromosome. So here try to understand flipping. So here a mutation chromosome of the same length as the chromosome is created with the probability p mu of 1s in the bit. For 1 in the mutation chromosome, the corresponding bit in the parent chromosome is flipped, that is 0 to 1 or 1 to 0, and mutated chromosome is produced. So that is offspring. So written as offspring here written as 1 0 1 1 0 0 1 0. So mutation probability is the same length. So that is the mutation chromosome. So that is O1 0 0 0 then 1 then 0 0 1. So here is 1, we need to flip it. So there is 1, there is 1, so there is 1. So we flip it. So that is 1. So now this is become to 0. So that is same 0 1 1. This is 1, so this is flipped. So that is 1. Next is 0 1. So next is 0, so it become 1. So that is mutated chromosome. You can try it with other example. So that is the first one by flipping. Second is that interchanging. So two position of a child chromosome are chosen randomly and the bit corresponding to these positions are interchanged. So here one chromosome is that 1 0 1 1 0 1 0 0. So choose the second bit from the most significant bit and this bit. So now they are interchanging. So this position goes there, this position goes there. So you'll get 1, this 1, 1, 1, then 0, 0, 0. So that is mutated offspring. That is by interchanging. Next is that the reversing. So a position is chosen at random and the bit next to that position is reversed to produce mutated offspring. So the offspring is that 0, 1, 1, 0, 0, 1, 0, 1. We choose this bit. So the next bit will interchange. So mutated offspring will be 0, 1, 1, 0, 0. This is 1, this is 1, 1. So these are the mutation technique for binary encoded genetic algorithm. The second one is that mutation in real coded genetic algorithm. So first one, random mutation. Here mutated solution is obtained from the original solution by giving a rule. So here rule is that P mutated equal to P original plus R minus 0.5 into delta. R is the random number lying between 0 to 1 and delta is the maximum value of approximate decided by the users. So delta is decided by the user, R is a number from 0 to 1. So an example is that P original is 15.6, random number 0.7, delta is 2.5. So here the formula will be P mutate equal to P original plus R minus 0.5 into delta. So here P mutate equal to P original, that is 15.6, plus R the number which is 0.7 minus 0.5, delta is 2.5. So here you will get it 16.1. So that is the P mutated. Now next is that polynomial mutation. So calculate a random number R lying between 0 and 1.0. Calculate the perturbation factor delta. So this formula is 2R 1 by Q plus 1 minus 1 if R is less than 0.5. This is 1 minus 2 into 1 minus R to the power 1 by Q plus 1 if R is greater than equal to 0.5. Q is assumed by the user. My formula is that P muted equal to P original plus this small delta into the capital delta is assumed by the user. So here P origin is 17.8, R is 0.7. So we need to use this formula. So here the Q is 2. So here delta will be equal to, by this formula, 1 minus 2 into 1 minus R, that is 0.7 to the power 1 by 3. So we'll get this number as 0.1565. So now P muted equal to P original plus small delta into capital delta, which is 1.2. So here P muted equal to by this formula, so that is P original, which is 17.8. Here P original is 15.6, no problem. So 17.8 plus 0.1565 into 1.2. You can calculate the value here. So where we assume this is 15.6 as the P original. So next one is that mutation for permutation encoding. You know that is applicable for traveling salesman, gym, job scheduling, and vehicle routing methods. So first one is swap mutations. So swap mutation is that you write one offspring. So that is offspring. This is something like A, B, C, D, E, F. So swap as the name suggests, swap as the name suggests. So take any two bits. So let's it the third and fifth bit. Third and fifth interchange their positions. So this is third, this is fifth. It will interchange their positions. So here you will get mutated offspring as A, B, E, D, C, F. So that is swap mutation. Next is that insertion mutation. So a number is that A, B, C, D, E, F. So pick the second one. So the second one, the second, so pick the second and place it in the fifth, and place or insert it, place it in the fifth position. So that is second, this is third, fourth, so fifth will be there. So it is A, C, D, E, fifth is now B, F. So that is insertion mutations. Next one is that flip mutations. Flip is that A, B, C, D, E, F. Take any bit and put in the last. So that is B, C, D, E, F, A. So that is flip mutations. Next is that scramble mutations. So here is that A, B, C, D, E, F. So B, C, D, so scramble it. So C, D, B, E, F. So this is the scramble mutations. Next one is that the you know that mutation in genetic algorithm is a vital component for ensuring diversity and preventing premature convergence, helping the algorithm to find optimal or near optimal solutions. It introduces random changes into the population's chromosome, keeping the search space dynamic. However, mutation should be used in moderation to maintain a balance between exploring new solutions and exploiting the good solutions that already exist in the population. So next one is that the termination and for convergence criteria. So each iteration should be tested with some convergence test. Commonly, convergence test or termination conditions are a solution is found that satisfies the objective criteria, then we will terminate the genetic algorithm, or fixed number of generation is executed. Suppose 50, so 50 is executed, we can stop it. Allocated computation time or memory reached. Allocated computation time oblique memory reached. The highest ranking solution fitness is reaching or has reached in a position such that successive iteration no longer produce better result, then we can stop it. The next one is that manual inspection, and last one is that combination of these conditions. So that is if you got the solution or fixed number of generations executed or allocated computation time or memory reached or no better result we are getting or manual inspection. So all these combinations we can do it. So it is observed that If fitness values are too far apart, then it will select several copies of the good individual and many other worst individual will not be selected at all. This will tend to fill the entire population with very similar chromosome and will limit the ability of the genetic algorithm to explore. If the fitness values are too close to each other, then the genetic algorithm will tend to select one copy of each individual. It will not be guided by small fitness variations and search space will be reduced. Now, one is the fitness scaling strategy. So, fitness scaling strategy is used to scale the raw fitness value so the genetic algorithm sees a reasonable amount of difference in the scaled fitness values of the best and worst. Fitness scaling is useful to avoid premature convergence and slow finishing. So few fitness scaling algorithms are there, that is linear scaling, sigma scaling and power law scaling. So linear scaling. So calculate the average fitness value, that is F bar, which is summation of I equal to 1 to n, or summation of all fitness, that is summation I equal to 1 to n Fi by n. Find F maximum, so maximum F where F is the all fitness, F is the set of all fitness, then find minimum, so F minimum, F minimum of F, so that is the same minimum values of all fitness value. Calculate a value A, which is F bar by F max minus F bar. B is that F multiply F mean divided by F mean by the F bar. So for each Fi belongs to F do Fi dash equal to A into F plus this B. And then initially F dash is 5. So F dash will be F dash union Fi 1. So then we can edit for better scaling. This should be the same, F bar equal to F dash bar. So that is for linear scaling. Now sigma scaling. Calculate F bar, that is summation I equal to 1 to n Fi by n. Determine reference worst case fitness value. So Fw equal to is that Fw is Fi bar plus S in multiplies sigma. So sigma is the standard deviation of the set F and S belongs to 1 to 5. So calculate Fi dash as follows. For each Fi belongs to F, do Fi dash equal to Fw, that is F worst minus Fi. Or if Fi greater than, if Fw is greater than Fi. Else Fi dash equal to 0. Discard the individual with fitness value 0. So that is the sigma scaling. Now power law scaling. So scale the fitness value is Fi dash equal to Fi k, where k is the problem dependent constant. So these are the technique of the scaling strategy. So now in conclusion, so in this class we have discussed the mutation technique, we have discussed mutation techniques for binary encoded, for real encoded and for order encoded. Second, we have discussed about the convergence criteria. And third one, we have discussed about scaling strategy, scaling procedures. So the question for today's class is that consider offspring O1. Question number 1, consider O1 in, that is binary code genetic algorithm. So 1 0 0 1 1 1 0 0. Find mutated chromosome by using all mutation techniques. By using all mutation techniques. Second is that O1, so that is something like 16.7. Find two different mutated chromosome by using mutation technique for real coded. Same technique for real coded. That is, you assume all parameters, all necessary parameters. Question number 3 is that assume offspring O1 for the order which is A, B, C, D, E, F, G, H. Find mutated chromosomes by using all mutation techniques. So solve these questions. So these are the references of today's class. Thank you.